A star's final breath can be a cataclysmic explosion or a silent fade to black. This cosmic choice governs stellar evolution, the very process that builds our universe and forges the elements of life itself. By the end of this journey, you will understand the precise cosmic rules that decide whether a star dies in a blaze of glory or vanishes into darkness. We will uncover why a star's initial mass locks in its destiny billions of years in advance, and reveal how the violent death of one star plants the seeds for new worlds. What does the silent end of a star like our own Sun reveal about the quiet cycles of the cosmos? Deep within the calm stability of a star's main sequence life lies a quiet, relentless battle. The immense weight of a star's own outer layers constantly presses inward, pulled by the unyielding force of gravity. At the very center, this crushing pressure creates a furnace of unimaginable heat, where atoms of hydrogen are forced together to create helium. This process, nuclear fusion, releases a torrent of energy in the form of light and heat, which pushes outward with tremendous force. For billions of years, this delicate stalemate holds. The inward pull of gravity is perfectly balanced by the outward push of radiation. A star like our Sun exists in this state of equilibrium for the vast majority of its life, shining steadily as it consumes its hydrogen fuel. But this fuel is not infinite. It is this simple, unavoidable fact, the gradual depletion of hydrogen in the core, that begins the chain of events leading to a star's final chapter. The entire fate of the star, whether it will fade or explode, hinges on what happens when this central furnace begins to flicker and the balance of power shifts irrevocably. The key to understanding this shift lies not at the surface, but in the secret reserves of fuel a star holds deep within its structure. This stable balance, however, is a temporary truce. The core is a crucible that is constantly consuming its own foundation. Every moment, countless hydrogen nuclei are fused into helium, and this new element is essentially ash from the stellar furnace. Unlike hydrogen, this helium ash cannot yet burn under the core's current conditions. It settles into the center, inert and heavy, while the fusion of hydrogen continues in a shell around this growing helium core. For a star like our Sun, this main sequence stability is a long and glorious summer, lasting for billions of years. But for a truly massive star, this period is a brilliant, fiery sprint. A star 10 times more massive than the Sun does not simply burn its fuel 10 times faster. It burns it with such ferocious intensity that its core fuel may be exhausted in just 20 million years, a cosmic blink compared to the Sun's 10 billion-year lifetime. The star's initial mass is its destiny, setting both its lifespan and the ultimate nature of its death. The moment the final reserves of hydrogen in the core are exhausted, that perfect balance shatters. The outward push of fusion falters, and gravity, patient and relentless, seizes its opportunity to crush the star inward. This collapse is not the end, but a violent new beginning, forcing the star to find a new, more desperate way to fight back. Gravity wastes no time. With the core's central furnace sputtering, the inward crush begins in earnest. The star's own immense weight, no longer held fully at bay, starts to compress the core. This is not a gentle squeezing. It is a violent act of collapse that transforms potential energy into intense, searing heat. The core, now a ball of inert helium ash, is subjected to this tremendous pressure, causing its temperature to skyrocket. But this heat does not stay contained. It radiates outward, superheating the thin shell of pristine hydrogen that still surrounds the core. Suddenly, that shell of fuel ignites. Hydrogen fusion, now raging in a spherical layer around the core, unleashes a far more powerful outpouring of energy than the core ever produced. This new, furious blast of radiation pushes the star's outer layers outward with irresistible force. The star begins to swell, its surface cooling as it expands to a staggering size. A star like our Sun becomes a red giant, its diameter swelling to engulf the inner planets. A more massive star becomes a red supergiant, an utterly colossal entity so large that it could contain millions of stars like our own. This magnificent inflation is the star's desperate response to its core's failure, a final, brilliant act of rebellion. Yet at the very center, the true drama is just beginning. The helium core itself is still collapsing, crushed into an ever denser, ever hotter sphere. It is this core and the incredible pressures building within it that will ultimately write the final sentence of the star's story. The core of a star like our Sun is now a sphere of pure helium, crushed by gravity into a state of incredible density. The temperatures here soar past 100 million Kelvin, a heat so extreme it forces the helium atoms themselves to fuse. This ignition is not a gentle process. It happens in a sudden, violent burst known as the helium flash, a runaway fusion event that, in mere seconds, converts vast quantities of helium into carbon and oxygen. This explosion is entirely contained within the core, and it provides a vital new source of outward pressure. For a time, the star finds stability again, settling into a calmer phase of helium burning. But this new lease on life is tragically short. The star is living on borrowed time, burning through its last significant fuel reserve. When the core's helium is finally exhausted, all that remains is a dense, hot ball of carbon and oxygen ash. Gravity resumes its relentless work, squeezing this core once more. The star desperately needs to ignite this carbon, to find one more source of energy to fight back. But a star of this modest mass has reached its limit. The crushing force is simply not enough to heat the core to the 600 million Kelvin required to fuse carbon. The furnace for the first time has gone permanently dark. With no new energy being generated at its heart, the star has lost its final battle against gravity's inward pull. The core can no longer support itself and begins a final, irreversible collapse. This fundamental inability to ignite another round of fusion is the quiet, cosmic reason these stars will never become supernova. Their fate is sealed not by a lack of will, but by a simple physical limit. Their journey now turns outward, away from the collapsing core, and toward the beautiful, gentle release of their own atmosphere into the void of space. This final, gentle release of a star's atmosphere is one of the universe's most breathtaking transformations. The star, no longer able to support its own outer layers, begins to pulse rhythmically like a cosmic heartbeat. These powerful vibrations, combined with a persistent stellar wind, slowly and gracefully push the star's gaseous envelope outward. The star is not exploding. It is unveiling itself. Over thousands of years, this expelled gas forms an immense, intricate shell around the central core, a structure we call a planetary nebula. The name is a historical accident, as these clouds have nothing to do with planets, but their beauty is undeniable. They glow with ethereal light, not from their own heat, but from the intense ultraviolet radiation blasting from the exposed stellar core now at their center. That tiny, hot core, once buried deep within the star, acts like a brilliant ultraviolet lamp, causing the vast clouds of gas to fluoresce in spectacular shades of red, green, and blue. Within these glowing clouds, we find the star's final chemical legacy. Elements like carbon and nitrogen, forged in the star's final fiery stages, are now scattered into space. This elegant process is how a star like our Sun returns its enriched material to the cosmos, a gift of raw materials for future generations of stars and planets. Yet this magnificent display is fleeting. A planetary nebula lasts for only a few tens of thousands of years, a mere moment in cosmic time, before its glowing gases disperse and fade into the darkness of the interstellar medium. The star's violent death has been averted, replaced by a slow, poetic unwinding. All that remains is the intensely hot, dense core now exposed to the void, an Earth-sized ember that will shine for trillions of years on its residual heat alone. But what happens when a star is too massive for such a graceful exit? What occurs when the core's collapse cannot be stopped, and the final battle against gravity triggers a far more violent and universe-shaking event? Left behind after the nebula's glow fades is the stellar core itself, now revealed as a white dwarf. This extraordinary object is the final, crystalline form of a star's heart. All that remains is a sphere of carbon and oxygen, but it possesses a density that is almost impossible to comprehend. Imagine taking the entire mass of our Sun and crushing it down into a sphere the size of Earth. Every single teaspoon of this material would weigh many tons, supported not by the fiery energy of fusion, but by a bizarre and fundamental force of the quantum world, a pressure that arises from the simple fact that electrons refuse to be squeezed into the same space. This is a star's final, stable form, a brilliant ember shining only with the immense heat trapped inside it from its active life. With no new energy being created, the white dwarf has only one path forward, a slow and irreversible cooling. It will shine with a faint, white-hot light for billions upon billions of years, gradually dimming through yellow and red as it radiates its warmth into the cold of space. Its ultimate destiny is to become a cold, dark, black dwarf, an invisible cinder drifting silently through the galaxy. This is the universe's most peaceful conclusion for a star, a fade into obscurity so gradual it is almost a form of eternal rest. Yet this quiet fate is not always guaranteed. Even these cosmic embers hold a secret potential for violence, a dormant power that can be awakened under the right and very specific circumstances. But this stable white dwarf state holds a critical vulnerability. Its existence depends entirely on a precise cosmic boundary, a number that dictates whether it will cool quietly or detonate violently. This is the Chandrasekhar Limit, a mass of about 1.4 times that of our Sun. It is the absolute maximum weight that the star's internal quantum pressure can possibly support. As long as the white dwarf remains below this threshold, it is safe, destined for that long, slow fade. But should its mass ever creep over that line, the delicate balance shatters instantly. The quantum pressure that has supported it for eons is suddenly overwhelmed by the sheer force of gravity. The star's own weight becomes its executioner, triggering a catastrophic, total collapse. This collapse is so rapid and so violent that it raises the core temperature to unimaginable levels, instantly igniting the entire star's worth of carbon and oxygen fuel in a single, simultaneous thermonuclear firestorm. There is no gradual burn. The entire white dwarf is consumed in a flash, completely torn apart in an explosion so powerful that not a single atom of the star remains. This is a Type 1, a supernova, a final blaze of glory for a star that had already accepted a quiet fate. What is truly remarkable is the consistency of this detonation. Because every white dwarf that crosses this mass limit is made of the same material and explodes in the same fundamental way, these supernovae always release nearly the same amount of light. For astronomers, this makes them cosmic lighthouses or standard candles. By observing how bright these explosions appear from Earth, scientists can calculate their distance with incredible precision, using them to measure the vast scales of the universe itself. This reveals a profound truth about stellar endings. A star's destiny is not always written in isolation. For a white dwarf in a binary system, a nearby companion star can act as a cosmic siphon, slowly transferring its own hydrogen gas onto the dense dwarf surface. Over millennia, this stolen mass accumulates, pushing the white dwarf closer and closer to its fatal limit. A star once destined for darkness is, through this stellar partnership, resurrected into a final, universe-calibrating flash of light. For a truly massive star, this journey through fusion is a desperate race against its own gravity. Each new element forged in its core provides a temporary reprieve, a new source of energy to hold back the crushing weight. Helium burns to carbon, carbon to neon, and so on, each reaction requiring even more extreme heat and pressure than the last. The star's interior transforms into a layered cosmic forge, with shells of different elements burning simultaneously, stacked like the layers of an onion. In the outermost shell, hydrogen fuses into helium. Deeper in, a shell of helium fuses into carbon. Below that, carbon burns, and so on, all the way down to the core. This is how these colossal stars become the universe's primary chemical factories, manufacturing the very elements that make up our world and even our own bodies. The oxygen we breathe, the calcium in our bones, the silicon in rocks, all were forged in the furious hearts of stars that lived and died long before our sun was born. But this prolific creation carries a terrible price. Each new stage of fusion burns faster and hotter than the last. The silicon burning phase, for instance, might last less than a single day, a frantic, final blaze of element creation. At the very center of this intricate, layered structure, the star is building its own doom, element by element. The final product of this cosmic assembly line is iron. Iron marks the final, unbreakable barrier in a star's life. For millions of years, nuclear fusion has been the star's ultimate power source, a process that always released more energy than it consumed. But fusing iron into heavier elements shatters this fundamental rule. It is a cosmic trap. The act of forcing iron atoms together does not release energy, it demands it, drawing power directly from the star's core. This transforms the iron core from a source of strength into a parasitic drain, an energy sink that starves the star of its last defense against gravity. The outward pressure that has held the star aloft for its entire life vanishes in an instant. With no force left to resist it, gravity wins the battle in a single, decisive moment. This is the iron catastrophe. A core that was once the size of our entire planet, containing more mass than our sun, is completely overwhelmed. In less than a second, this colossal structure implodes. It collapses at speeds approaching a quarter of the speed of light, crushed from a vast sphere down into an unthinkably dense ball of neutrons only about 20 kilometers across. The sheer violence of this implosion is difficult to grasp. It is as if a star's entire heart is being forced through a keyhole. This is the precise, terrifying instant a core collapse supernova is born. Yet this incredible implosion is only the first act of the drama. The core's collapse is so sudden and so complete that it sets the stage for an even more powerful and paradoxical event, a final, defiant rebound that will tear the rest of the star apart. The star's iron core has become a trap, and its collapse is now unstoppable. As it implodes, the pressures reach a scale that defies everyday understanding. Within this crushing environment, the very building blocks of matter are forcibly rearranged. Protons and electrons, which normally repel each other, are squeezed together with such violence that they merge, transforming into neutrons. This process releases a ghostly flood of neutrinos, particles so tiny and non-interactive they usually pass through entire planets without a single bump. But here, in the heart of this cataclysm, the density is so overwhelming that even these ghost particles are momentarily trapped. They are bottled up inside the collapsing core, their collective energy building into an unimaginable pressure cooker. This is a crucial turning point. The star's final hope for a rebound does not come from fire, but from this ghostly pressure and a sudden, profound change in the nature of matter itself. The collapsing core, now a seething ball of neutrons, continues to be compressed until it reaches a density comparable to that of a single atomic nucleus. At this exact moment, a new and unyielding force emerges. The core suddenly becomes rigid, a perfect sphere of nuclear matter so dense it cannot be compressed further. The immense wave of material still falling inward from the outer layers does not gently settle. It smashes into this newly solidified surface and rebounds with shattering force. This is the core bounce, combined with the pent-up neutrino pressure now bursting free. This rebound triggers a titanic shockwave. It is this shockwave that becomes the true engine of the star's destruction. It blasts outward from the core at incredible speeds, a wall of pure energy that rips through the star's elaborate onion-like layers. In a final, violent act, the star is torn asunder. Its outer layers, now packed with all the newly forged elements from carbon to uranium, are hurled into the depths of space at thousands of kilometers per second. This is not merely an explosion. It is a cosmic dispersal mechanism of breathtaking efficiency. The destruction of one star becomes the raw material for countless new ones, seeding nebulae with the ingredients for future solar systems and ultimately for life itself. How does the universe manage to preserve a remnant from such utter devastation? And what bizarre object is left spinning in the wake of this cataclysm? What remains after the star has been utterly annihilated is far from empty space. The debris from the explosion, a searingly hot cloud of gas and dust laced with newly forged elements, races outward at thousands of kilometers per second. This expanding shell, a supernova remnant, becomes a cosmic recycling center on a truly epic scale. For thousands of years, this structure will continue to grow, its intricate filaments glowing with the trapped energy of the blast and the heat from radioactive elements created in that final instant. The famous Crab Nebula is a perfect example of this beautiful chaos, a tangled web of light that represents the ongoing dispersal of a star's elemental legacy. Within this hot, expanding gas are the very atoms that were synthesized during the star's life, and in its violent death, elements like oxygen, silicon, and iron. This is the primary mechanism by which the universe is enriched, as these heavy elements are scattered into the vast interstellar medium, the raw material between stars. This enriched gas is the fertile ground from which future generations of stars and planets will eventually coalesce, but the remnant's role is not passive. The immense shockwave that precedes the expanding debris plows through surrounding clouds of cold, quiet gas like a cosmic bulldozer. This wave can compress the gas, disturbing its delicate balance and triggering gravitational collapse in regions that might have otherwise remained dormant. In this way, the death of one star can directly initiate the birth of countless others, a stellar nursery born from the ashes of a catastrophe. A supernova, therefore, is not a final end but a critical transformation, a vital phase in the great cycle of stellar death and rebirth that continuously shapes and evolves our galaxy. The brilliant remnant will eventually cool, its glow fading over millennia as it disperses and merges completely with the interstellar medium, its constituent atoms destined to one day become part of new worlds and perhaps new life. The collapsing core, now a rigid sphere of neutrons, has withstood total annihilation. This is a neutron star, the universe's ultimate density champion. Born from the supernova's fury, it is a cosmic paradox. You are taking an object containing more mass than our entire sun and crushing it down to the size of a single city. The numbers involved are so extreme they defy any earthly comparison. A single sugar cube of this material would weigh billions of tons, a mass equivalent to every single person on our planet compressed into a tiny speck. This incredible density arises because the star's collapse has eliminated virtually all empty space, packing atomic nuclei together until they touch. The entire structure is in essence a single, gigantic atomic nucleus. The creation of this object is so violent that it inherits the raw energy of the explosion itself. A newborn neutron star spins at a dizzying rate, completing multiple rotations every single second. Its magnetic field, already intense in the progenitor star, becomes concentrated and amplified to an almost mythical strength, trillions of times more powerful than Earth. It is from this combination of rapid spin and intense magnetism that one of astronomy's most useful tools emerges. If the neutron star's magnetic poles are misaligned with its rotation axis, it can act like a cosmic lighthouse. Beams of intense radiation, from radio waves to X-rays, shoot out from its magnetic poles. As the star spins, these beams sweep through space. If one of those beams happens to cross Earth's path, our telescopes detect a regular, repeating pulse. We call such a star a pulsar, and its rhythmic ticking is one of the most precise clocks in the universe. This allows astronomers to study the effects of gravity on spacetime itself and to navigate the cosmos with incredible accuracy. The neutron star stands as a triumphant monument, a remnant that successfully fought gravity to a standstill using the fundamental forces of quantum physics. Yet for the very largest stellar cores, this triumph is only temporary. There exists a mass so great that not even the combined might of a city-sized sphere of neutrons can resist the final, all-consuming pull of gravity. There is a final, unbreachable threshold where even the neutron star's defiant stand fails. When the collapsing core of a star contains more than 3 times the mass of our entire sun, it crosses into a realm where the known laws of physics cease to function. The quantum pressure that holds up a neutron star, the last and most powerful force of resistance in the universe, is utterly overwhelmed. The collapse does not slow or stop or find a new equilibrium. It continues forever. The core, once a brilliant city-sized sphere of neutrons, is crushed into a single point of infinite density, a concept so alien we call it a singularity. The sheer mass of this vanishing point warps the fabric of spacetime around it, creating a gravitational pit so deep that nothing, not even a beam of light traveling at the universe's ultimate speed limit, can ever climb back out. This is the birth of a black hole. The point of no return is marked by an invisible boundary known as the event horizon, a perfect sphere surrounding the singularity. It is not a physical surface you could touch, but a one-way membrane in the geometry of the cosmos. Any matter or energy that crosses this threshold is lost forever to our observable universe, its information trapped behind an eternal curtain of gravity. The formation of a black hole represents gravity's ultimate and absolute victory over every other force. While the outer layers of the star are still being blasted outward in a spectacular supernova, the heart of the star simply winks out of existence, leaving behind only its immense, silent gravitational influence as a monument to a star that was simply too colossal to leave any other remnant. The universe classifies its stars by a single, brutal metric, mass. This initial weight, determined in the stellar nursery, writes a script for the star's death that will play out billions of years later. The critical dividing line falls at around 8 times the mass of our Sun. Any star born lighter than this will, after a long and stable life, exhaust its nuclear options and gently shed its atmosphere, leaving behind a white dwarf. It is a quiet, predictable end, but cross that 8 solar mass threshold, and the star's fate shifts from a quiet fade to a violent climax. These heavier stars possess the gravitational might to push their cores all the way to the creation of iron, triggering the core collapse supernova that forges neutron stars. The story, however, does not end there. For the true titans, those born with more than about 25 solar masses, the final collapse is so overwhelming that not even a neutron star can form. Their cores are so heavy they cross a point of no return, collapsing directly into black holes. These numbers are not absolute laws but cosmic guidelines, a framework that reveals a universe governed by predictable physical principles. A star's spin, its magnetic personality, and even its chemical makeup can nudge the final outcome, but mass remains the primary author of its destiny. This leads us to a fascinating question. If mass is the main character in this story, what role does a star's chemical composition play in its final act? Mass, however, is not the only author of a star's fate. There is a hidden ingredient in this cosmic recipe, a chemical signature inherited from the cloud of gas that gave the star its birth. This is a star's metallicity, a term astronomers use not for common metals, but for any element heavier than helium. From the oxygen we breathe to the iron in our blood, these are the metals of the cosmos, and their initial abundance within a star creates a profound ripple effect that shapes its entire life and the nature of its death. Our own Sun is a perfect example of a metal-rich star, known as a population 1 star. These stars are the universe's younger generation, formed from gas that has already been seeded and enriched by the ashes of countless prior supernovae. For these stars, a higher metallicity is not a trivial detail. Those extra heavy elements make the star's outer layers more opaque, which in turn affects how effectively the star can shed its own atmosphere through a persistent stellar wind. Imagine a star constantly exhaling a fraction of itself into space. Over millions of years, this steady mass loss can be significant, gently whittling down the star's total weight before its final dramatic act. This means a metal-rich star might enter its death throes with a considerably lighter core than it started with, a factor that could be the difference between forming a neutron star and collapsing entirely into a black hole. Now travel back in time to the older, more pristine era of the universe. Here we find population 2 stars, ancient suns that burn in the halos of galaxies and within dense globular clusters. These stars are metal-poor, possessing only a tiny fraction of the heavy elements found in our Sun. Their chemical simplicity has a direct consequence. With fewer heavy elements to make their atmospheres opaque, their stellar winds are far weaker. They hold onto their mass with a tenacious grip, unable to shed their outer layers as effectively as their metal-rich cousins. A population 2 star may therefore live its entire life and arrive at the moment of core collapse still bearing nearly all of its original mass. This retained mass could lead to a more powerful supernova or the formation of a more massive remnant, a silent testament to how a star's chemical frugality can amplify its final, violent release. But what of the very first stars? The hypothetical population 3 stars are the universe's true pioneers, formed from a cosmic soup of only hydrogen and helium, completely devoid of any heavier metals. Theorists suggest that this pure, simple composition allowed them to grow to almost unimaginable sizes, perhaps hundreds of times the mass of our Sun. Without metals to help them cool and fragment, they accumulated matter in a way that modern stars cannot. Their deaths, however, are predicted to be the most bizarre of all. In stars of such immense mass and purity, the core temperatures become so fantastically high that the radiation itself begins to spontaneously create pairs of electrons and their antimatter counterparts, positrons. This process, called pair instability, robs the core of its supporting radiation pressure in a sudden and catastrophic way. The result is not a quiet fade or a standard core collapse, but a runaway thermonuclear explosion of a completely different class. A pair instability supernova is so utterly violent that it can completely obliterate the star, leaving no remnant behind, not even a black hole. The entire star is vaporized, scattering its pure, primordial fusion products into the waiting universe. This act of total self-sacrifice by the first stars was likely what provided the initial, crucial enrichment of heavy elements that allowed all subsequent generations of stars, and eventually planets like our own, to form. A star's chemical ancestry, therefore, is a deep and often overlooked layer in the cosmic rulebook, a subtle variable that whispers across billions of years to influence the very nature of a star's final breath. This gravitational partnership can become a cosmic waltz with deadly consequences. Many stars are not solitary beacons but exist in pairs or small groups, bound together by their mutual gravity in a delicate, eternal dance. This proximity means their life stories are deeply intertwined, and the gravitational tug of war between them can rewrite their individual destinies. When one star in a binary system ages and swells into a red giant, its outer layers become gravitationally vulnerable. The companion star can act like a cosmic thief, siphoning off this gaseous material and pulling it onto its own surface. This process, known as mass transfer, can dramatically alter the life cycle of both stars. The donor star is stripped of its envelope, prematurely revealing its hot core, while the recipient star is suddenly gifted with a fresh supply of hydrogen fuel. This can effectively rejuvenate the receiving star, extending its life or triggering new phases of nuclear activity. But this stolen gift can also be a curse. If the recipient is a white dwarf, the accumulated mass can push it over the Chandrasekhar limit, that critical threshold of 1.4 solar masses. This triggers a runaway thermonuclear explosion that completely obliterates the white dwarf in a Type 1, a supernova, a brilliant standard candle used to measure the cosmos. In other tightly bound pairs, a massive star might have its entire hydrogen envelope ripped away by its voracious partner long before it can naturally shed it. This leaves behind a bare, exposed stellar core, which then proceeds to its own supernova, but one that looks distinctly different in our telescopes, lacking the hydrogen signature of a typical explosion. The most extreme outcome of this stellar dance occurs when both stars are already corpses. The slow, in-spiral and eventual merger of two neutron stars creates ripples in spacetime itself, gravitational waves that we can now detect. This violent collision is also a primary cosmic forge for the heaviest elements in the universe, creating vast clouds of gold, platinum, and other precious metals in a single, glittering cataclysm. These dynamic interactions reveal a profound truth. A star's fate is not always a solitary, predetermined path. It can be a shared narrative, a story of theft, renewal, and violent partnership that unfolds over billions of years, proving that in the cosmos, no star is ever truly an island. A brilliant supernova flashes in a distant galaxy, and to the untrained eye, it is simply a new star where none existed before. But for astronomers, that pinpoint of light is a complex message, a cosmic telegram written in the language of physics. To decode it, they turn to two critical tools, the supernova's spectrum and its light curve. The spectrum is like a chemical fingerprint, created by splitting the light into its constituent colors. Dark lines that appear at specific wavelengths reveal the unique signatures of elements present in the exploding material, telling scientists what the star was made of when it died. This single measurement allows for the most fundamental classification. If the spectrum shows no sign of hydrogen, the most common element in the universe, the event is labeled a Type 1 supernova. If strong hydrogen lines are present, it becomes a Type 2. This simple distinction points toward completely different catastrophic mechanisms, but the spectrum is only the beginning. The full story unfolds over time, written in the supernova's changing brightness. This is the light curve, a graph that plots the explosion's brilliance from its sudden peak to its slow fade into darkness. The shape of this curve, how quickly it rises and how slowly it decays, holds vital clues about the energy source that powered the blast and the specific elements created within it. A Type 1, a supernova, born from a white dwarf's total disintegration, has a famously predictable light curve. It brightens incredibly rapidly as radioactive nickel is forged in the explosion, and then it decays in a very specific way as that nickel decays to cobalt and then to iron. This consistency is what makes them such perfect standard candles for measuring the universe. In stark contrast, the light curve of a Type 2 supernova, the classic core collapse of a massive star, tells a different tale. Its brightness is initially powered by the immense energy of the shockwave ripping through the star's outer layers. After the peak, the decline is slower, as the glow is maintained by the heat from radioactive elements interacting with the extensive, hydrogen-rich debris that was once the star's atmosphere. This lingering light is a direct result of the star dying with its outer envelope still intact. Yet, the story grows even more intricate within the Type 1 category. The absence of hydrogen is the unifying trait, but the presence or absence of other elements reveals the progenitor's identity. A Type 1 shows silicon in its spectrum, the hallmark of a white dwarf's composition. But what of Types 1b and 1c? These are not thermonuclear explosions at all. They are also core collapse supernova from massive stars, but stars that have been stripped bare. A Type 1b supernova lacks hydrogen but still shows helium, pointing to a massive star that lost its outer hydrogen envelope, perhaps to a voracious companion star. A Type 1c goes a step further, missing both hydrogen and helium, suggesting the progenitor was stripped down to its core, a bare ball of heavy elements like oxygen and carbon before its collapse. This elegant classification system transforms a single flash of light into a detailed stellar autopsy report. By reading the light curves and spectral lines, astronomers can determine not just how a star died, but what kind of star it was, what it was made of, and what extraordinary circumstances led to its final, brilliant performance. These brilliant historical events were not just celestial curiosities, they were profound cultural milestones. The supernova of 1054, for instance, was meticulously recorded by court astronomers in China as a guest star, a brilliant new light in the constellation of Taurus. It was visible in broad daylight for 23 consecutive days and remained a fixture in the night sky for nearly 2 years. This same event was also noted by Arabic scholars and potentially by Native American cultures, its image perhaps preserved in rock art. This was the violent birth of the cosmic object we now call the Crab Nebula, a direct link between an ancient astronomical record and a vibrant, modern-day supernova remnant. Centuries later, in 1572, the Danish nobleman Tycho Brahe witnessed another such star, blazing brighter than Venus in the constellation Cassiopeia. His precise measurements proved it was located far beyond the Moon, a direct challenge to the ancient Aristotelian belief in an immutable and perfect celestial sphere. Then, in 1604, Johannes Kepler observed his own supernova, an event that captivated Europe and was studied without the aid of a telescope. These historical sightings shattered a philosophical dogma that had persisted for nearly 2,000 years. The heavens were not a static backdrop. They were a dynamic, changing arena where stars could be born and could die in spectacular fashion. This realization was a crucial intellectual shift, helping to clear the path for the scientific revolution and the modern study of the cosmos. Today, these ancient observations provide an incredible gift to science, a known timestamp for some of the galaxy's most fascinating objects. Astronomers can study the expanding debris of the Crab Nebula and know exactly how old it is, 1,070 years old. This allows them to measure the velocity of the expanding shockwave, calculate the energy of the original explosion, and observe the behavior of the pulsar at its heart with a precise historical context. These few recorded supernovae in our galactic backyard remind us that the great stellar cycle is not a remote abstraction. It is a living process that has directly intersected with human history, its light reaching the eyes of our ancestors and fundamentally altering our understanding of our place in the universe. That predictable flash of light from a dying star became the key to measuring the cosmos. When a white dwarf crosses its critical mass limit and detonates as a Type 1, a supernova, the physics of its total disintegration ensures every single one of these events reaches nearly the same peak brightness. This uniformity makes them perfect standard candles, cosmic lighthouses whose distance can be measured with extraordinary precision. The principle is beautifully simple. If you know how bright a light bulb truly is, you can calculate how far away it is by how dim it appears. Astronomers do the same with these supernovae. By comparing their faint, observed glow to their known, intrinsic brilliance, they can determine their distance from Earth, charting the vast emptiness between galaxies. This reliable tool allowed for a discovery that shattered our understanding of the universe. In the late 1990s, two independent teams were observing extremely distant Type 1, a supernova, expecting to measure how much the universe's expansion was slowing down due to gravity. To their astonishment, they found the opposite. The most distant explosions were fainter than predicted, meaning they were farther away than anyone had thought. The universe's expansion was not slowing, it was accelerating, as if some mysterious, repulsive force was pushing galaxies apart at an ever-increasing rate. This invisible driver, now called dark energy, earned the researchers the Nobel Prize and rewrote the textbooks of cosmology. The violent death of a star, a predictable cosmic bomb, had illuminated the fate of the entire cosmos, revealing that the universe is dominated by a force we cannot see and barely understand. This profound connection shows that by studying how stars end their lives, we are ultimately reading the story of the universe's own birth, its long evolution, and its final, mysterious destiny. The scattered debris of a supernova is far more than a beautiful remnant. It is a cosmic forge of incredible power. Within the searing heat and unimaginable pressure of the expanding shockwave, a frantic and prolific act of creation takes place, a process known as explosive nucleosynthesis. The sheer violence of the blast slams atomic nuclei together with such force that they fuse into entirely new, heavier elements. It is here, in this fleeting moment of stellar destruction, that common atoms are transformed into the building blocks of rocky worlds. Elements like silicon, the primary ingredient of sand and rock, sulfur, and the calcium that forms our bones are violently minted in the supernova's fiery wake. But the creation does not stop there. For the very heaviest elements in the universe, a different, even more exotic process is required. In the neutron-rich environment immediately following the core collapse, a phenomenal event unfolds called the rapid neutron capture process, or the R process. Atomic nuclei are bombarded by a dense flood of free neutrons, absorbing them faster than they can radioactively decay. This rapid assembly line builds atoms upward in weight, step by frantic step, creating elements that are otherwise impossible to forge in the calm heart of any living star. It is through this specific cataclysm that rare and precious elements are born, including silver, uranium, and gold. Every ounce of gold in a wedding ring or a microchip was once part of the chaotic, neutron-dense debris from a colliding star or a supernova that lit up the cosmos eons ago. This scattered stardust, now enriched with these newly forged elements, eventually drifts into vast molecular clouds. Over millions of years, gravity pulls these clouds together, and within them, new stars and planetary systems begin to coalesce. Our own solar system formed from such a cloud that was seeded with the chemical legacy of countless stellar explosions that occurred long before the sun was born. This means the oxygen that fills your lungs with every breath was forged in the core of a massive star. The iron that carries life, giving oxygen through your bloodstream, was created in a star's final moments. The very calcium that strengthens your bones was cast out into the galaxy by a supernova's explosive force. We are, each and every one of us, a living collection of atoms that were created in the hearts of stars and distributed across the light years by their spectacular death. The existence of life, of our planet, and of our own bodies is a direct consequence of stellar death. This profound connection reveals a universe that is not only vast but deeply interconnected, where the end of one ancient, colossal star becomes the necessary beginning for everything we know. Even the most brilliant stellar finales can sometimes be a cosmic dud. For the true titans of the starry realm, those born with immense mass, the final collapse can be so total and efficient that the star simply implodes without a trace. This is the realm of the failed supernova, sometimes called an unnova. In this silent scenario, the star's core collapses directly into a black hole, just as expected. But the shockwave that should rebound and tear the star apart never makes it out. Instead of a triumphant rebound, the immense inward flood of material from the outer layers proves too overwhelming. The nascent shockwave stalls, its energy drained as it tries to plow through a near-infinite amount of falling star stuff. All of that incredible energy is simply used to keep feeding the newborn black hole, which hungrily consumes the entire star from the inside out. There is no titanic explosion, no brilliant flash to announce the star's passing. From our distant vantage point, it would appear as if a massive, luminous star that had shone for millions of years simply flickered and vanished from the heavens. Its light permanently extinguished the moment its surface crossed the newly formed event horizon. Imagine watching a lighthouse for years, only for it to suddenly go dark forever, leaving no wreckage behind. How could we ever hope to witness such a non-event, the ultimate cosmic stealth exit? Astronomers search for these ghosts by staring at patches of the sky where massive stars were known to exist, looking for the telltale disappearance. A few compelling candidates have emerged, where a star was clearly present in earlier surveys, and then was simply gone in later observations, with no supernova detected in between. This silent collapse represents the ultimate victory of gravity, a force so absolute it can swallow a star's death cry before it ever reaches the void. It is a profound reminder that the universe holds mysteries where even the most violent of endings can be rendered completely mute. The very laws of physics can turn a star's core into its own executioner. For the most colossal stars, those born with a staggering 130 to 250 times the mass of our Sun, a uniquely self-destructive process awaits, one that leaves absolutely nothing behind. This is the pair Instability supernova, a fate dictated not by a core of iron, but by the strange and paradoxical behavior of pure energy itself. Within these stellar giants, the core temperature climbs to such an unimaginable extreme that the radiation trapped inside undergoes a bizarre transformation. The photons, the very particles of light that provide the outward pressure holding the star up, suddenly become massive enough to spontaneously create matter. In a flash, they convert into pairs of particles and their antimatter counterparts, electrons and positrons. This act of creation is the star's undoing. By converting radiation into matter, the core instantly loses the radiation pressure that was its primary support against gravity. It is as if the floor of a building suddenly vanished. The core undergoes a violent partial collapse, but this implosion is not like any other. The sudden increase in temperature and density from this collapse is so extreme that it instantly ignites the star's entire supply of oxygen in a single, simultaneous thermonuclear blast. There is no shockwave rebounding from a solid core. There is no delicate balance. The entire star is consumed from the inside out by a runaway fusion reaction that no structure can contain. The explosion is so utterly violent that it completely unbinds the star, blasting every single atom of its being out into space. Not a single speck remains to form a neutron star or a black hole. The star is entirely vaporized, annihilated in a final act of cosmic self-sacrifice. These events are so energetic they can outshine entire galaxies, and they are thought to have been the spectacular finales for the universe's first generation of stars, those pure hydrogen and helium giants. In their total self-destruction, they provided the initial, crucial enrichment of heavy elements that paved the way for all the diverse stars and planets that would follow. The serene symmetry of a star's life is utterly shattered in its final moments. We often picture these explosions as perfect spheres of light, but the reality is far more chaotic and dynamic. The collapse of a star's core is not always a uniform implosion. Instabilities deep within the dying star can cause the collapse to be fundamentally lopsided, a stagger rather than a straight fall. When the rebounding shockwave erupts, it does not push outward with equal force in all directions. This inherent asymmetry, often driven by the chaotic flow of neutrinos and matter, imparts a tremendous recoil to the newborn neutron star at the center. It is literally kicked like a cannonball fired from a cosmic cannon. This natal kick can propel the stellar remnant at unbelievable velocities, often hundreds and sometimes over 1,000 kilometers per second. We observe these rogue neutron stars, these pulsars, racing across our galaxy on solitary paths, their rapid motion a permanent record of the unbalanced violence of their birth. In the most extreme cases, this asymmetry focuses into incredibly powerful and narrow beams. Rather than a sphere of expanding debris, the star's death channels immense energy into two opposing jets of matter and radiation, screaming outward at velocities approaching the speed of light. These are not gentle streams, but the most powerful particle accelerators in the universe, blasting through the star's outer layers and punching holes straight through the expanding debris. This focused fury is thought to be the engine behind some of the most luminous events we have ever witnessed, the spectacular gamma-ray bursts. For a brief moment, these jets can outshine the combined light of every star in a billion galaxies, a final, focused scream of a star whose internal collapse was anything but ordinary. These chaotic, three-dimensional deaths remind us that the simple, spherical diagrams in textbooks are a pale shadow of the true, messy reality. The universe prefers complexity, and every unbalanced explosion adds a new layer of mystery to our understanding of how the largest stars meet their end. Our ability to witness the final moments of stars is about to leap forward in an extraordinary way. We are entering the age of multi-messenger astronomy, a time when we will not only see these cosmic explosions but also hear and feel them across the fabric of reality. This new era is powered by a suite of revolutionary observatories, each designed to capture a different part of the story. The Vera C. Rubin Observatory, for instance, will act as the ultimate cosmic surveillance camera. With its immense mirror and gigantic camera, it will scan the entire visible sky every few nights, discovering thousands of new supernovae each year. More importantly, it will catch them in their infancy, often within hours of their light first reaching Earth, giving us an unprecedented look at the very first instance of a stellar death. Once this all-seeing eye finds an explosion, other instruments will zoom in for a closer look. The next generation of giant segmented mirror telescopes, like the extremely large telescope, will dissect the light from these events with breathtaking precision. Their incredible spectra will reveal the chemical composition of the blast in minute detail, allowing us to trace the distribution of newly forged elements with the clarity of a cosmic map. But light is only one part of the narrative. The universe sends its most violent messages through spacetime itself. Gravitational wave observatories like LIGO and Virgo are listening for the ripples produced by the asymmetrical collapse of a stellar core or the final, spiraling dance of two neutron stars about to merge. These detectors allow us to literally feel the vibrations of these distant cataclysms, providing a physical sense of the forces involved that light alone cannot convey. And then there are the ghostly messengers. Neutrino telescopes buried deep underground or under the Antarctic ice are on constant watch, waiting for the telltale flash from the next supernova within our own galaxy. When a massive star's core collapses, the vast majority of its energy is carried away by a torrent of these nearly massless particles. Detecting that sudden burst would give us a direct, real-time signal from the heart of the collapse itself, an unedited view of the moment a neutron star or black hole is born. By combining the sight from new telescopes, the sound from gravitational waves, and the feel from neutrino pulses, we will assemble a complete, multi-sensory picture of stellar death for the very first time. This integrated approach promises to transform a brilliant flash in the night from a simple spectacle into a rich, dimensional story, revealing the inner workings of the universe's most powerful engines. This cosmic cycle of creation and destruction carries a sobering implication for any world caught in the crossfire. The brilliant flash of a supernova, so vital for seeding the galaxy with new elements, is also a sterilizing blast of unimaginable power. In an instant, the star's final breath transforms into a wave of pure death for any planetary system orbiting too close. The first signal of the catastrophe would not be a visible fireball, but an invisible surge of high-energy radiation. A torrent of gamma rays and X-rays would strike nearby planets at the speed of light, violently stripping electrons from atoms in their atmospheres in a process known as ionization. This would rip away the protective gaseous envelope that shields a world from stellar radiation and helps maintain a stable climate. Any life on the surface would then be bathed in a lethal dose of radiation, a silent, invisible apocalypse. The initial flash is only the beginning. Following close behind the physical debris of the star itself, a supersonic shockwave of incandescent gas and dust would arrive centuries or millennia later. This blast wave would physically scour the planetary system, while a relentless rain of cosmic rays would continue to bombard any surviving worlds for thousands of years, further poisoning the environment. The conditions necessary for life, so delicate and rare, would be utterly erased within a zone spanning dozens of light years. Our own solar system may have experienced a brush with such a disaster. Deep on the ocean floor, scientists have found a curious layer of sediment containing traces of a rare isotope, iron-60. This form of iron is not naturally made on Earth. It is forged only in the heart of a supernova and scattered into space by the explosion. The specific dating of this layer points to a nearby stellar collapse occurring around 2.6 million years ago, a time that coincides with a known period of mass extinction on our planet. While not the sole cause, it suggests a celestial event may have contributed to a period of great hardship for life on Earth, a distant echo of a star's death influencing our own world's biological story. For a planet in orbit around the star that explodes, there is no question and no escape. The world would be vaporized, its very atoms torn apart and assimilated into the expanding remnant. This stark reality highlights the precarious nature of existence on a cosmic scale. The same violent death that forges the elements for new worlds and future life can, in the same stroke, erase all of it. A supernova is never an isolated event. It is a galactic reset button, capable of sterilizing entire regions of space and forcing the long, slow clock of biological evolution to start anew somewhere else under safer, quieter stars. The chemical ghosts of long-dead stars linger all around us. We do not need to wait for a new explosion to witness this ancient cycle, for the history of our galaxy is written in the very atoms of its oldest suns. This is the field of stellar archaeology, a way of reading the galactic fossil record. Astronomers point their telescopes toward ancient, metal-poor stars that have been shining for over 12 billion years. These are the stellar equivalent of time capsules, formed from the pristine hydrogen and helium of the early universe, but with one crucial addition. Trapped within their atmospheres are the minute chemical impurities inherited from the very first stellar explosions. By splitting the light from these ancient stars into a spectrum, scientists can measure the precise amounts of elements present, from carbon and oxygen to rare heavy metals. Each specific pattern of elements acts as a chemical fingerprint, revealing the nature of the supernova that forged them. A certain ratio of iron to oxygen might point to the violent death of a single, massive star, while an abundance of lighter elements like carbon and magnesium could suggest the explosion came from one of the universe's first, fantastically large progenitors. These chemical signatures are the final, enduring messages from stars that died before our own sun was even born. They tell us that the earliest supernovae were not all the same. Some produced vast amounts of certain elements while lacking others, painting a picture of a chaotic and diverse beginning to our galaxy's chemical enrichment. By reading these faint spectral lines, we can reconstruct the mass distribution and death styles of the Milky Way's first generations of stars. The galaxy we see today, with its mix of young metal-rich stars and ancient metal-poor ones, is the direct result of this long chain of stellar life and death. Each supernova contributed its unique elemental signature to the interstellar mix, like a chef adding a distinct ingredient to a cosmic soup that would eventually form new stars, planets, and us. This forensic study of starlight reveals that our existence is built upon the layered legacy of countless stellar explosions, a story of cosmic renewal written in the language of chemistry itself. The violent chaos of a stellar core's collapse cannot be captured on a simple chalkboard. To truly understand the milliseconds when a star's fate is decided, scientists construct entire stars inside a computer. These are not simple animations, but full-scale virtual laboratories governed by the unbreakable laws of physics. The challenge is immense, requiring models that simultaneously track the complex interplay of supersonic fluid dynamics, the ghostly flow of trillions of neutrinos, the frantic blaze of nuclear reactions, and the twisting of magnetic fields of almost mythical strength. Only the world's most powerful supercomputers, running calculations for months at a time, can hope to simulate such a multi-faceted cataclysm in 3 dimensions. These digital stars are our proving grounds, the crucial bridge between elegant mathematical theory and the brilliant, messy reality we observe through our telescopes. They have revealed that a perfectly spherical star would almost never explode. The key to a successful supernova lies in the star's internal turbulence. As the core collapses, it does not fall smoothly. It sloshes, it churns, it convulses. This roiling motion, combined with the intense heating from the trapped neutrinos, revives the stalled shockwave. The shock begins to bubble and bulge like a pot of water boiling over in a phenomenon known as the standing accretion shock instability. It is this inherent, beautiful asymmetry, this chaotic sloshing of matter and energy, that ultimately gives the shock the push it needs to tear its way out through the star's layers. Without this turbulent revolt against perfect symmetry, the shock would fail, and the star would silently collapse into a black hole. Every run of these monumental simulations is a test of our fundamental understanding of the universe, refining our knowledge of how the most massive stars complete their life cycle and, in their final, turbulent moments, gift the cosmos with the seeds of new worlds. From the quiet cooling of a white dwarf to the universe-shaking blast of a supernova, we see a cosmos governed by elegant, predictable rules. The life and death of every star is a story written by its initial mass, a chemical signature inherited from its birth cloud, and the gravitational dances it shares with its stellar neighbors. These are not random acts of cosmic chaos, but the direct outcomes of the immutable laws of physics playing out on a galactic stage. We have journeyed from the peaceful, poetic unwinding of a planetary nebula to the violent, chaotic birth of a black hole, witnessing how each endpoint serves a vital purpose in the great cycle of the universe. The carbon in a diamond, the oxygen in the air we breathe, the iron that courses through our veins, all were forged in the hearts of stars and scattered across the light years by their spectacular deaths. We are, in the most literal sense, made of star stuff, a living testament to cosmic events that occurred long before our world was born. This profound connection transforms the night sky from a static tapestry into a dynamic story of continuous transformation. The faint glow of a distant nebula is not just a beautiful cloud, it is the birthplace of future suns. The darkness between the stars is not an empty void, but a reservoir of ancient stardust, the raw material for everything to come. The next time you gaze upward, remember you are looking at a universe of endless endings and beginnings, where the death of one star is a necessary gift, sowing the seeds for new worlds and ultimately for us. If this journey through stellar life and death has expanded your view of the cosmos, we would love to hear your reflections in the comments. For more explorations into the wonders of space, be sure to subscribe.